Hey team, I'm Maddie. Welcome to Science Side Up, and today we are talking about lifting condensation level. In the last two videos, we learned about moist and dry adiabatic lapse rate. What we're gonna do today is bring those two things together and use them in a very classic Meteorology 101 type homework problem, which is a mountain problem. And then we're also going to use those to understand a meteorological term called the LCL, which stands for lifting condensation level. Definitely keeping my notes in my hand for this video because you don't want to see me try to do math live. I will inevitably say something very silly. That is why we have notes. So the basic setup for this problem is we have a mountain. In order to do this problem, we need to know a few things. We need to know how high the mountain is, and we need to know the surface temperature and dew point on this side of the mountain. So this would be the windward side of the mountain. For this problem, our mountain is going to be 2,500 meters high, so 2.5 kilometers. My surface temperature on this side of the mountain is going to be 25 degrees Celsius, and my dew point is going to be 13. So let me get a different color of chalk to differentiate those two temperatures. And if I forget to write my units, all of my temperatures today are going to be in degrees Celsius. Okay, so now we need a couple more numbers. One, our dry adiabatic lapse rate, which is going to be 10 degrees Celsius per kilometer. And my moist adiabatic lapse rate, if you guys remember from the last video, that actual number depends on how much water vapor you have in the air, but we're going to use 5. And then the last thing that we need to know is how does dew point decrease with height? How is that affected by height? And that number, a good rule of thumb for that is going to be 2 degrees Celsius per kilometer. Now let's talk real briefly about kind of physically what's going on. So if we're thinking about this, think of this as like the Sierra Nevada mountains and Seattle is over here, right? So global surface winds at that latitude are going to be coming from west to east. So we have global winds that are coming this way, and then they hit the mountains, and if they hit a mountain, they can't go through it. So they're going to end up being forced up and over. In this case, my terrain acts as a lifting mechanism for all of this incoming air. And this air, it's coming from over the Pacific Ocean, so you know it's got a ton of water in it. So this setup is actually about as physically in the real world as close as you're going to get to our lifting an air parcel thought experiments that we've been doing throughout the last several videos. Last thing I'm going to do is mark some specific heights where we're going to be interested in temperature and dew point. Forgive me, I didn't space my lines out quite enough, I guess, but I marked every 500 meters going up the mountain, and then, let's see, I carried that over, we'll bring that over to this side of the mountain. Okay. So now what we want to do is figure out what temperature and dew point are going to be at each one of these levels. Okay, so at the surface, we have 25 degrees Celsius with a dew point of 13. I'm warmer than dew point, so I am not saturated yet. So my air parcel is going to cool by my dry adiabatic lapse rate. Now, since we're only going half a kilometer, 500 meters, this is only going to drop by 5 degrees. So my 25 degrees Celsius is going to become 20. And dew point, which changes by 2 degrees per kilometer. So in these 500 meters, it'll only drop by 1. This drops down to 12. And if it wasn't clear, white is temperature, yellow is dew point. Well, at 500 meters, I'm still warmer than dew point. So let's go up another 500 meters. My dew point is going to go down to 11. and my temperature drops by another 5 degrees. So now this is 15. I'm still warmer than dew point, so let's just do it again. 10 and 10. So when you're doing these problems, it is important to just calculate temperature and dew point at every level, because if you don't, you might miss this point. So at about 1.5 kilometers up in the atmosphere, my air parcel has cooled to its dew point. So this means my air is now saturated. And from this point moving up, we're going to use moist adiabatic lapse rate. And because the air parcel is now saturated, my dew point is going to follow the temperature of the air parcel. So it's no longer gonna follow this relationship, because we know if we're following the moist adiabatic lapse rate, the air parcel must be saturated. If it's saturated, temperature equals dew point. So now when I go up another 500 meters, I'm not gonna drop 5 degrees Celsius, I'm only gonna drop 2.5. So this is now 7.5. And my dew point follows. Going up that last 500 meters, we're gonna stay saturated. So we get down to 5 and 5. Now, before we come down the other side of the mountain, let's talk about this side for a second. The lifting condensation level is this point. It's where my temperature first equals dew point, the height at which my air parcel first becomes saturated. And if there are no other processes going on, then we would expect clouds and precipitation starting at this height. So my lifting condensation level can be a representation of the height of the cloud base, right? And then this is also why Seattle is very, very rainy, because this moist air coming in from over the Pacific runs into a mountain and is forced up, bringing all of that moisture with it. And so we're gonna get a lot of rain here. Now that brings us to this side of the mountain. We actually call this side the leeward side, whereas the side that the wind is hitting is the windward side. So an assumption that we make in mountain problems, and is a pretty good approximation of the real atmosphere, is that once the air reaches the top of the mountain, all of its water vapor has been condensed into clouds over here. So the air coming down the mountain is going to be dry, and we're gonna follow my dry adiabatic lapse rate and my normal value for the change in dew point. So let's bring these 5 degrees Celsius that we are at the top of the mountain down 500 meters. So that means, and now that we're coming down, we're gonna warm instead of cool, right? So my temperatures in white is going to increase by 5 degrees in those 500 meters. So it's up to 10. And my dew point is only gonna increase by 1, so it's at 6. If we drop down a full kilometer, temperature becomes 20, dew point is 8, and then getting all the way down to the surface, temperature is 30, and dew point is 10. So this is something else that we can know about the general climate of areas like whatever is east of Seattle. It tends to be warmer and drier at the surface than our windward city counterpart. To sum this whole problem up, 1, what is lifting condensation level? The lifting condensation level is the lowest height where an air parcel becomes saturated. How do I do a mountain problem? Well, I'm gonna start on my windward side of the mountain at the surface. I'm going to let temperature decrease by the dry adiabatic lapse rate until I hit the lifting condensation level, and then it will drop according to the moist adiabatic lapse rate. When I come down the leeward side of the mountain, I'm going to use the dry adiabatic lapse rate. And that's how you do a mountain problem. Okay team, that's all I've got for you today. I hope you liked this video, and I will see you all in the next one. Bye team! My parcel of air will have dried. Nope, not dried, cooled.